Our goal now is to study quantum Hall effect in graphene. So to do that, the most appropriate geometry to perform that task is the one-dimensional geometry. So we open quantum honeycomb and we press the 1D button. And we return to this window that we already know. So the simplest way to put magnetic field in a tie-binding model is through the Peierls substitution, and that parameter in the Hamiltonian is precisely the magnetic field one. So in here we are going to put 0.5 magnetic field, 0.05 magnetic field, and we are going to calculate the magnetic structure, the electronic structure of our system, and we get something like this. So if we zoom in our bands, we will see that we have something like flat bands in here and then dispersive bands in there. We can easily see this if we increase the size or the magnetic field of our system. So for example, we are going to increase the magnetic field, we are going to calculate again the band structure, and we are going to see is that the flat part is actually bigger than before. So this is what we have. We have the flat band here and dispersive bands in here. To see where these states are located, the easiest way to do so is to calculate the expectation value of our wave function. So we change the band's color into position 1, we calculate again ground state, and we show the band structure. And what we are going to obtain now is the same as before, but with the bands colored according to the expectation value of the state. So for example here, green means that we are in the bulk, red that we are in the edge, and blue that we are in the edge. So we see that these states are located in the bulk, and in here there is a state located on the edge and another state located on the edge. Something pretty interesting of a zigzag ribbon is that these flat bands in here are not, at least not all the states are located on the bulk. And this can easily seen if we add a small sublattice imbalance, something like this. So we calculate ground state, we calculate band structure again, and what we will see is that whereas part of these states are located in the bulk, so these states in here are Landau levels, these states in here are located on the edge, and these are actually the children of the states that lived on the edge for the zigzag ribbon without magnetic field. So these in here are Landau levels, these in here are the edge states that we had even before the magnetic field. To see a system that doesn't have this kind of weird behavior, we could move on to a armchair ribbon. So we are going to decrease a bit the magnetic field, we are going to increase a bit the geometry of the system, we are going to calculate the ground state and show the band structure again. And in this system what we are going to see is that all the flat bands are going to be actually Landau levels in comparison with the zigzag ribbon that had some flat band which wasn't a Landau level. So this is what we get here. We see that all the parts that are flat are also green, so that means that they are Landau levels and they are located on the edge of your system. Whereas these states here that are dispersive, they live in the edges. And something pretty interesting is that these states live in different edges. So if you count how many electrons are going to the right, at this energy, what you see is that there's only one electron which goes to the right. And there's another electron which goes to the left, but which is located in the opposite edge. This means that if there's some kind of impurity on your edge and you think that your electron is going to be able to do backscattering by interacting with that defect, you are wrong, because the state to come back is located just in the other edge, and you cannot jump across your whole ribbon just to get to the state which propagates in the opposite direction that you were propagating. You can easily see that if you plot what is the density of states of your system. So what you see is that, well, in the density of states you have to change the energy, so we are going to put 0.4 for our energy, for the energy that we want to see. And at 0.4 you see that your states are located in this edge and in this edge. And these states are moving in this direction and these states are moving in this direction. So an electron which is moving this direction, if it tries to backscatter by jumping here, he can't. The state is really far. And to see how is the density of states of this flat band, we can just put this energy of this flat band, which is 0.1 in here, and what we are going to see is that these states are actually located in the bulk in here, in comparison with the states before that were located purely on the edge. So this is at energy 0.4, this one, whereas this one is the first Landau level, and as you see are purely located on the bulk and are non-dispersive, as you can see here. So this is the end of our brief tutorial about Landau levels. Thank you very much.